Now let's talk about increasing and decreasing functions. Let's just kind of look at it logically for a minute. Suppose I have a function that goes up for a while and then goes down for a while. It doesn't matter how smooth that is. I'm going to have a relative maximum. Well, if I have a function that goes down and then goes up, I'm going to have a relative minimum. Now, suppose I have a function that goes only up. It doesn't matter how smooth or bumpy that might be. As long as it's going up on both sides of any given point, I have neither a maximum nor a minimum. Similarly, if I have a function that's going down and going down some more, so that it's always decreasing on either side of a point, then I don't have a maximum or a minimum. So whether a function is increasing or decreasing is very important. So here's a definition, and all definitions get written in your notebook. A function is increasing on an interval if for any two numbers x1 and x2 in the interval, x1 being less than x2 means f of x1 is less than f of x2. All right, so for any two numbers, x1 and x2, all right, because x1 is less than x2, that implies f of x1 is less than f of x2. And indeed, that is what an increasing function looks like. Well, let's look at a decreasing function. A decreasing function tells me for any 2 points, x1, and x2, x1 is less than x2, and by the way, x1 is pretty much always less than x2. Okay, means that f of x1 has got to be greater than f of x2. Or rather, that is, the value of x1, f of x1 is greater than the value of f of x2. Now, I want to throw something in right here because it's going to get a little confusing if you're not very careful. F of x1 and f of x2 can be negative. If this entire graph were slid down, okay, the same functions would apply. If this is negative, that's all right, because f of x1, say, equal -1, and f of x2 is -10, it turns out that indeed -1 is greater than -10. So you have to look at how the function is moving. Okay? All right. Now, to test for increasing and decreasing functions, if f is continuous on the closed interval and differentiable in the open interval, then if f prime is positive, f is increasing on the closed interval. If the derivative is negative, then f is decreasing on the interval. And if f is 0, then it's a constant. Let's just do a quick proof here. Let's assume that f prime of x is positive for all x in the interval ab, in the open interval ab, and let x1 be less than x2. We do that a lot. Be any 2 points in our interval. By the mean value theorem, MVT, we know there exists a C such that x1 is less than C is less than x2, so C is between x1 and x2, and f prime at C, which is f evaluated x2 minus f evaluated x1 divided by x2 minus x1. Now, because this is positive and x2 minus x1 is positive, Therefore, f of x2 minus f of x1 is also positive, or f of x2 has to be greater than f at x1. The other proofs follow pretty simply. Now, let's get to the meat of it. How do we use this to show intervals where f is increasing or decreasing? Now, you can look at the graph, but you won't get exact answers off a graph necessarily. So the first thing we want to do is take the derivative. So I'm going to take the derivative, f prime at x. This is 3x squared minus 3x. All right, now I want to factor it. Now this is going to factor very nicely. X times x minus 1. And I want to see, where does this equal 0? Well, it equals 0 at x equals 0 and at x equal 1. All right. Now, f exists at all the points, so I can conclude that these are the only two critical numbers that I have to deal with. So let's look. Let's see, I've got 0 and then I've got 1. So let's look from negative infinity to 0. So my first interval is going to be all x from negative infinity to 0. Now, let's look between 0 and 1. Between 0 and 1. And then our third region is going to be, of course, from 1 to infinity. I threw myself off because I gave myself an extra column. All right, so basically what you're going to do is break it up into the three regions, 1, 2, 3, or into the regions. Separate it by your critical points. All right, let's test the value. Okay, you can pick any value you want. All right, and we can pick, you don't want to pick an endpoint. So let's pick, oh, it doesn't matter what we pick. Let's pick negative 1. All right, f prime at negative 1 is 3 times negative 1 minus 1. So that's 2 times 3 is 6. That becomes positive, so this is positive 6. All right, so f prime at negative 1 is 6, and that's positive. Because the derivative is positive, I know it's increasing. Between 0 and 1, you can pick any point you want, but let's pick f prime of 1/2. And I'm showing you every step here. So 1/2 minus 1. Okay, and this is, well, that's negative 1/2. And negative 1/2 times 1/2 is 1/4. So this is negative 3/4. See, I'm using 1/2. And f prime at 1/2 is 3/4 negative. Okay, and because this is less than 0, it's decreasing. Now from 1 to infinity, you can pick any point you want. Oh, but let's just pick 2. It looks like that's going to give us a fairly nice number. F prime at 2, I remember I'm doing 2, is equal to 6 times 2 minus 1. Oh, that is easy. All right, that's 6, and this is positive. So the sign is positive, and so this is increasing. All right, so f is increasing from negative infinity to 0. All right, it is decreasing between 0 and 1, and then it's increasing from 1 to infinity. Give it a go. Tell you what, before you do that, let me give you some summaries. Write these guidelines down. All right, let f be increasing on the interval to find the open interval in which f is continuous on the interval. To find the intervals on which f is increasing or decreasing, locate the critical numbers, determine the sign of f prime, and then use theorem 3.5 to determine whether f is increasing or decreasing on each interval. And then put everything in these forms. Now, go back to this, complete this. When you're done, finish your homework.